Most of the dilations you're going to have to perform in class are going to be performed on the coordinate plane. Now, the coordinate plane has a couple distinct advantages over just free drawing a dilation. For one, you don't need to use a ruler. The measurements are provided to you in the form of the grid itself. However, as we should already know, there are limitations to those measurements. They can only be in the cardinal directions, up, down, left, or right. That means diagonal lines are going to have to be reinterpreted in terms of their cardinal directions. A dilation scale factor multiplies all lengths and distances. That includes the cardinal directions. So, to apply the scale factor in a diagonal direction, we're going to apply it to each of the cardinal directions individually. Together, that will end up applying the scale factor to the total distance. For example, if we are dilating line AB, which is this little black line right here, we're dilating it from center A, so outward this way. It's going in a diagonal direction. So how are we going to be able to figure out how long to make these dilations without using the ruler, measuring how long the line is, and then doubling that length? Well, we're going to use the cardinal directions to help us out. Even though A to B is a diagonal line, it has cardinal direction distances of 3 to the right and 1 up. That means that if we apply the scale factor of 2 to each of those numbers individually, we end up with 6 to the right, 6 to the right and 2 up. If we apply those individually, 1, 2, 3, 4, 5, 6 to the right, and 1, 2 up, then we land at a new spot, which is exactly twice the length of the original line. That's the way all this works. We can do it again with multiplying by 3, a scale factor of 3. If we know, once again, that the original length, the original cardinal directions are 3 to the right and 1 up, then we can triple each of those values and go 9 to the right and 3 up. We go 9 to the right and 3 up, and we end up in the exact perfect spot for tripling the length of that diagonal line. Let's put it into practice with a couple shapes. Here we have a hexagon. We're dilating it from center M. Now, most of the time on the coordinate grid, you're not going to be provided with the pink guidelines. Those you can add yourself, though. They can be useful for helping you to determine, in general, where your new points should end up. You're still going to want to use the cardinal directions to find the exact locations, but the guidelines can be a lot of help to make sure that you're on the right track. In general, if you draw accurate guidelines, you should have the satisfaction of finding that your endpoints land right on those dotted guidelines. So, for instance, if I am dealing with an original hexagon and I want to apply a scale factor of 2, that means I'm doubling all the distances. Now, some of these distances are just in the cardinal direction, so those are super easy. Here we have 1, 2 to the left. Well, that's going to become 4 to the left. It's going to double. Here we have 2 down. That's going to become 4 down. Here we have 2 up. That'll become 4 up. Here we have 4 to the right. That's going to become 8 to the right as it gets doubled. Now we still have 2 diagonal distances to take care of. So let's look at each of them. Well, from M to this point, it's 1, 2 to the right and 1, 2 up. So we can put down that it's 2 to the right and 2 up. And if we multiply each of those by 2, we end up with 4 to the right and 4 up. And if we apply that, 1, 2, 3, 4 to the right and 1, 2, 3, 4 up, we end up right on the dotted line, right where we want it to be. Same token, to get to this point, it's 1, 2 to the right and 1, 2 down. So if we're doubling each of those, that becomes 1, 2, 3, 4 to the right and 1, 2, 3, 4 down to get our final point. And from there we can complete our new hexagon, where every length and every distance is double what it was in the original black hexagon. We could also go the other way around. We could go with a scale factor of 1/2. I'm going to use purple for that since I already used the red. So for scale factor of 1/2, for cardinal directions, that's once again easy. We know that half of 2 is 1. So instead of going 2 to the left, we're only going 1 to the left. Instead of going 2 up, we're only going 1 up. Instead of 2 down, we go 1 down. And instead of 4 to the right, we're only going 2 to the right. We're going halfway. For our diagonal distances, we once again have 2 to the right and 2 up. Well, if we're dividing both of those values by 2, we end up with 1 to the right and 1 up. So if we go from the center 1 to the right and 1 up, then we land here. And for the other one, if we go 1 to the right and 1 down, then we end up halfway as well. And here's our little mini hexagon. Boop. All right. Last one for this, we're going to do a 3 times scale factor of 3. So what's our 2 going to turn into? 2 times 3 is 6. So we'll go out 6. Once again, we'll go 2, 4, 6. Downwards, 2, 4, 6. To the left, we're going 4, 8, 12 is 4 times 3. And then for our diagonals, well, we've got 2 to the right times 3 is 6 to the right. 2 up times 3 is 6 up. So 1, 2, 3, 4, 5, 6 to the right, and 1, 2, 3, 4, 5, 6 up lands us up there. For the other one, 6 to the right and 6 down lands us down here. And I'll draw my new hexagon right through my map because it's so gigantic. But that's okay. Kind of looks like a fun little spider web. Or a tunnel. All right, one last one. We're going to focus in on fractional scale factors. Now, fractional scale factors are just like any other scale factor. You should know by now that a fraction is a number divided by another number. It's the numerator, the top number, divided by the bottom number. So if we're multiplying by a scale factor, then that means that we are multiplying by the numerator and then dividing by the denominator. So if we're talking about 1/5, that means that whatever our cardinal directions are, we're going to multiply them by 1 and then divide them by 5. So let's start from T. Let's go to A. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to the left. That's 10 to the left. And 1, 2, 3, 4, 5 down. So if we put that in our math, we know that 10 times 1/5. 10 times 1 is still 10. Divided by 5 equals 2. 2 to the left. Our 5 times 1/5, well, 5 times 1 is still 5. Divided by 5 gets us 1. So our massive 10 to the left and 5 down turns into a measly 2 to the left and 1 down for our copy. So I'll put on the purple, 1, 2 to the left, and 1 down. And there's our little bitty A prime. For B, we're starting out with 1, 2, 3, 4, 5 up. 1, 2, 3, 4, 5 to the left. As we just did with the math, 5 times 1/5 is 1. So we are going to just do 1 up and 1 to the left to get B prime. And finally, C is on the cardinal direction, so that should be easy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We know that 10 times 1/5 is 2, so we just go 2 to the right to get C prime. And there's our little bitty triangle with a 1/5 scale factor. Now, what if it's a fraction that doesn't have a numerator of 1? Well, as I said, it's multiply by the numerator and then divide by the denominator. So if we're starting once again with 10 and 5, 10 times 3/5, well, 10 times 3 is 30. 30 divided by 5 is 6. 6 to the left. 5 times 3 is 15. Divided by 5 is 3. So 5 turns into 3. So if we go 1, 2, 3, 4, 5, 6 to the left, and 1, 2, 3 down, we end up with a double prime for the scale factor of 3/5. For B, we're starting out with 5 and 5. Each of those 5s is going to turn into a 3. So 1, 2, 3 up, and 1, 2, 3 to the left. And there's our B double prime at that spot. And then for C, we're starting out with 10. 10 times 3/5 is 6. So we're going to go 1, 2, 3, 4, 5, 6 out to the right to get C double prime. And here's our 3/5 triangle. Notice how in both cases, our new triangle is smaller than our original. As we talked about in the overview, if you have a fraction for a scale factor that is smaller than 1, you're going to decrease the size of the object. But number 3, that's not the case. In number 3, our scale factor is 6/5. 6 is greater than 5. That means that this fraction's value is greater than 1, meaning that our new triangle is going to be larger than the original. So let's start with A. A, we have 10 to the left. We're going to multiply that by 6/5. 10 times 6 is 60. 60 divided by 5 is 12. The 5 down. 5 times 6/5. Well, 5 times 6 is 30. 30 divided by 5 is 6. So our A prime should be 12 to the left and 6 down from the center. So we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then 6 down. 1, 2, 3, 4, 5, 6. There's a triple prime. For B, 5 and 5 is going to turn into 6 and 6. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's B triple prime outside of B. And then for C, we know that 10 is going to turn into 12. So we'll go 2, 4, 6, 8, 10, 12 to the right for C triple prime. And we'll make our huge triangle. By the way, drawing these triangle copies is easier when you know, whoop, didn't do it right that time, is easier when you know that each of your new lines is going to be parallel to each of your old lines. That's a fun feature of dilations, is that parallelism is retained between corresponding lines. All right, so that's all for the coordinate plane. Please let me know if you have any questions.